of the lecture tutorial, the part about killing the sun. So once helium runs out in the core, the sun's got a core of carbon and oxygen, mostly carbon, but some oxygen. There's no fusion happening there, and there will never be any fusion because the contraction of the core is stopped by a new kind of pressure that does not come from fusion. It's a kind of pressure called degeneracy pressure that comes occurs when you try to pack electrons, in particular, too close to each other. And so pressure is still balanced with gravity inside of that core, but the difference now is that the pressure is not coming from fusion, the pressure is coming from this degeneracy pressure. Around that, you've got a shell of material that's hot enough to fuse helium into carbon, and around that, a shell that had been fusing hydrogen into helium. And at this point, a star like our sun will be so large that it extends all the way out to the Earth's orbit. And you never quite get to a stable phase here. The fusion sort of pulses on and off. And these pulses have a couple consequences. One is that you start to blow off the outer layers of the star into space. So along the way, the Earth will get cooked. In about 1 billion years, the sun will have heated up enough that it's likely that the Earth will not be inhabitable. Again, it's in 1 billion years, so 1,000 million years, far, far, far in the future. This slow dimming of this, or slow change in luminosity of the sun has absolutely nothing at all to do with climate change. By the time the sun becomes a red giant, it'll be putting out more than 10 times as much energy as it is now. And at that point, Earth's oceans will boil off if they haven't already, and the surface becomes unlivable. And there's a series of additional thermal pulses beyond that. So again, what evidence do we have that this is the case? These thermal pulses blow the outer layers of the star off into space, making what's called a planetary nebula with a white dwarf, which is the core of the star that created the nebula, left behind. And there's several examples of these. We can measure the content of the gas in the planetary nebula, which gives us insight into the fusion processes that are happening inside or happened in the past in that material. These things can have different shapes and sizes, but and can change shapes as they're growing. So this planetary nebula initially was round, and then later waves of ejections of material were not round. So a little bit more about observations. From what we've talked about so far, you should be able to convince yourself that 2 solar mass stars will go through their hydrogen fuel faster than 0.5 solar mass stars. Think of the bonfire analogy again. A bonfire burns hotter, but it also consumes its fuel faster. And so that 2 solar mass star is going to be much more luminous than the sun. It'll use up its fuel much faster. The 0.5 solar mass star will go through its fuel much less quickly. And as a result of this, the shape of the main sequence, if you look at a group of stars that all form together, the shape of their main sequence or the HR diagram will change over time. So we're starting here with something like 100 or 200 stars in a model star cluster, and we're showing the HR diagram as the stars form. This shows stars of all kinds of masses. And what we're going to see in a moment here is that as time goes on, first the high mass stars, which are also higher temperatures, the ones in the upper left, are going to leave the main sequence much more rapidly than the low mass, cooler stars in the lower right. In this simulation, these stars are not moved onto the red giant area of the diagram as soon as they leave the main sequence. They're just taken off the picture. So you can see the stars in the lower right are still actually joining the main sequence, and you can see that while those low mass stars are still becoming stars, the higher mass stars have already started to leave the main sequence and head up to be giants. We're at about 40 billion years now, so most of the stars that are going to form have formed. The high mass stars are starting to leave more and more rapidly. Time is also speeding up here to keep the simulation bearable, and we're just about to the point here. There's where solar mass is leaving the main sequence at about 10 billion years, and after 20 billion years, you still have some stars left on the main sequence, the very low mass ones. To look at the bigger picture here, the this is a HR diagram for a star cluster. You can see the main sequence, but you can also clearly see the track where stars have moved up to become red giants. Some stars in the very upper right are ready to undergo their helium flash, and the horizontal branch, or that you see around 100 solar masses, is the stars in which helium is being fused into carbon and oxygen in their core. Okay, that's it. We'll be back in the classroom next Tuesday, and I'll be available online all weekend, so let me know if you have any questions.